Hello students, welcome to Swapna physics classes. In this lecture I am going to explain you one more chapter from 10th class physics, and the chapter is refraction of light at curved surfaces. And this chapter includes types of curved surfaces, ray diagram for the curved surfaces, and a derivation of curved surface formula, and lenses and its types, and the terminology related to the lenses, and the ray diagrams and image formation for the lenses, and then after we will derive the lens formula and lens maker formula. And coming to the topic, refraction of light. Refraction of light is possible whenever a light ray incident the interface of the two different mediums. For example, I'm considering a plane surface. This plane surface divides two different mediums. That is, for example, on one side of this plane surface we have the rarer medium. And I'm taking this rarer medium as air, and on the another side of this plane surface we have the denser medium. Okay. This plane surface divides both these mediums. Okay, this acts as the interface between these two mediums, and here the denser medium is the water. I am taking the denser medium as the water. Okay, and if this is the normal to this plane surface, what is the normal for a plane surface? If you draw a perpendicular line to this plane surface, then this line is known as the normal. Okay, and at this point I am taking an incident ray. This is the incident ray at this point, and this incident ray makes an angle I with the normal. Okay, whenever a light ray travels from the rarer medium to the denser medium, it will move towards the normal. Okay, after refraction, what happens? The light ray will bend towards the normal. Okay, and this refractor ray makes an angle R with this normal. Okay, this is the incident angle, this is the refracted angle. Okay, you have to remember one thing: whenever a light ray travels from the rarer medium to the denser medium, the light ray after refraction will move towards the normal, will bend towards the normal. Okay, and I will give one more example, and I am taking a plane surface. Here the light ray is traveling from the denser medium to the rarer medium. From denser medium to the rarer medium. Okay, and if this is the normal to this plane surface, and this is the incident ray at this point. Okay, this is the incident ray at this point, and I is the angle made by this incident ray with this normal. After refraction, what happens? The refractor ray will bend away from the normal. This refractor ray will bend away from the normal, and it makes an angle R with this normal. Okay, this is about plane surface. The refraction of the light by plane surface. Now, what about the curved surface? The refraction of the light by curved surfaces. Let's see. We have the curved surface or spherical surfaces. The spherical or curved surfaces are of two types. Spherical surfaces. Okay, spherical surfaces are of two types. One is concave surface, and the other is convex surface. And the terminology related to these concave and convex surfaces are terminology. First of all, you have to know the terminology related to these convex and concave surfaces. Then only you will be able to draw the ray diagrams. Okay, and the terminology related to these spherical surfaces are center of curvature. One is center of curvature. I will explain one by one. Okay, and the other is pole. pole, principal axis, principal axis, refractive index, refractive index, focal length, focus point, all these are related to these curved surfaces only. Okay, and coming to this center of curvature, if this is a curved surface which divides or which acts as the interface between two mediums, that is, this is the interface between the denser medium and the rarer medium, and the geometrical center or the midpoint of this curved surface is known as pole, and it is denoted with P. Okay, and if you extend this curved surface, you will observe the sphere, right? Here we have a sphere, and the center of the sphere is known as the center of curvature of this curved surface, and it is denoted with C. The center of curvature of this curved surface is nothing but the center of the sphere. Okay, and if you draw a line that which joins the pole and this center of curvature, this line is known as principal axis. Principal axis. Okay, this is principal axis. And coming to refractive index, what is refractive index? The refractive index describes the refractive index describes how fast the light ray travels through the medium. Okay, how fast a light ray is traveling through the medium is described by this refractive index, and it is denoted with N. And according to Snell's law, if this is a curved surface we have, okay, and this is the pole of this curved surface, and this is the center of curvature for this curved surface, and here we have the rarer medium and here we have the denser medium. We just assume, okay, and the refractive index for the rarer medium is N1 and the refractive index for the denser medium is N2. Then the ratio of the refractive index of these two mediums, that is N1 by N2, will be equals to sine of angle of incidence to the sine of angle of refraction. In our syllabus, there is no definite derivation for this equation. Therefore, I am not deriving this equation. Okay, and if this is the incident ray, okay, and this is the normal at this point. This incident ray makes an angle I with this normal. Okay, and after refraction, what happens? This refracted ray makes an angle R with this normal. Okay, the refractive index of medium 1 to the refractive index of medium 2 will be equal to sine of the angle of incident to the sine of the angle of refraction. This is about Snell's law. Okay, and coming to the ray diagrams for curved surfaces. Okay, according to Snell's law, actually whenever the light ray that which travels traveling along the normal will not deviate from its path. from its path. ఈ deviation అంటే ఏంటి? Bend అవ్వడం. Okay, from its path, will not bend. Deviation is nothing but bend from its path. Okay, this is given by Snell's law. Okay, whenever the light ray is traveling along the normal, this ray will not deviate from its path. I will give you one example. For example, I am taking a convex surface. This is the convex surface, and on this side I have the rarer medium, and on this side I have the denser medium. This is the denser medium we have. Okay, this is the denser medium we have, and the refractive index of the rarer medium is n1. I am taking it as n1, and the refractive index for the denser medium I am taking it as n2. And this is the pole, this is the center of curvature for this curved surface. And if this is the normal, what is the normal for the curved surface? The line which joins the center of curvature and the surface of this curved surface is known as the normal. If you extend this on the other side, if you extend this line on the other side, and I am considering a ray which is passing through this normal, I am considering a incident. If this is the incident ray which is passing through the normal, then this ray after refraction will not bend. Okay na, ఇది bend అవ్వదు. ఈ డైరెక్షన్ లో గానీ ఈ డైరెక్షన్ లో గానీ bend అవ్వదు. It will pass through the normal only. It will pass through the normal only. This is the refractor ray. This is the incident ray. This is the refractor ray. It will not deviate from its path. It will pass through the normal only. Okay, and I'm taking one more ray which is passing through this principal axis. This principal axis is also one of the normals, right? Why? Because this principal axis is passing through the point on the surface, passing through the line which joins the point on the surface and the center of curvature, right? Therefore it is also a normal, right? And if this is the incident ray, after refraction what happens? The ray will move in the same path only. The ray will move along the normal only. It will not deviate, it will not bend after refraction. Okay, and we have four more ray diagrams. I'm taking them as case 1, case 2 and case 3. Okay, case 1 for convex mirrors or convex surface. Okay, convex curved surface. And if this is a convex curved surface, okay, and this is the denser medium for this convex surface, and this is the rarer medium, and this is the denser medium, and this is the center of curvature, and this is the pole. I am taking a parallel ray. If this is the ray which is parallel to the principal axis, and this ray is incidenting this curved surface at some point, and after refraction this ray bends towards the normal. Where is the normal? Here at this point, this will be the normal, right? Whenever a light ray travels from the rarer medium to the denser medium, after refraction what happens? This ray will bend towards the normal. Okay, and coming to case 2 for convex mirror or convex curved surface. Okay, I'm taking a convex surface, and this convex surface acts as the interface between the denser medium and the rarer medium. Here I have the denser medium, okay, and here I have the rarer medium. This is the denser medium and this is the rarer medium. Whenever a light ray is passing from the denser medium to the rarer medium, okay, I am considering a parallel incident ray. This ray is parallel to this principal axis. Okay, this is the incident ray, and after refraction what happens to this refractor ray? For this purpose I am considering the center of curvature and a normal at this point. This is the normal at this point. And this is the incident ray. After refraction, what happens? Whenever a light ray travels from the denser medium to the rarer medium, this refractor ray will bend away from the normal. This refractor ray will bend away from the normal. Whenever a light ray travels from the rarer medium to the denser medium, the refractor ray will bend towards the normal. And whenever a light ray travels from the denser medium to the rarer medium, the refractor ray will bend away from the normal. Okay. And if you extend this refractor ray in backward direction, what happens? This refractor rays will meet at some point on this principal axis, right? This point is known as focal point, which is denoted with capital F. Focal point or focus. Focus or focal point. Okay, focal point. And coming to the concave mirror or concave curved surface. And coming to concave curved surface, case 3, okay, for concave curved surface. Okay, I am taking a concave curved surface. For a concave curved surface, this is the denser medium we have, okay, and this is the rarer medium. And the light ray will incident in this direction for a concave mirror. Why? Because concave mirrors or concave surfaces are bulged inward. This will be the reflecting or refracting surface. Okay, whenever a light ray travels from the denser medium to the rarer medium, this is the incident ray, and if this is the center of curvature, this will be the normal at this point, at this incident point, and I am just extending this normal on the other side. Okay, and as the light ray is traveling from the denser medium to the rarer medium, this light ray will bend away from the normal. See, this light ray will bend away from the normal, and this refractor ray will meet at a point on the principal axis. This point is known as focus point. Okay, and coming to the next case, case 4, for concave mirrors, for concave surfaces. Okay, and this is the concave surface which acts as the interface between the denser medium and the rarer medium. Okay, this is the denser medium and this is the rarer medium. I am considering again a parallel ray. This is the incident ray, and at this point this will be the normal for this curved surface. This is the center of curvature, this is the pole. Okay, and I am just extending this normal on the other side. Whenever a light ray travels from the rarer medium to the denser medium, the light ray will bend towards the normal. The light ray will bend towards the normal after refraction, right? This will bend towards the normal. And if you extend this refractor ray on the other side, this ray will meet at some point on this principal axis. This point is known as focus point. Okay, you have to remember one thing, that is, whenever a light ray travels from the rarer medium to the denser medium, what happens to the refractor ray? The refractor ray will bend towards the normal. Whether it is a convex surface or concave surface or a plane surface. Okay, and whenever a light ray travels from the denser medium to the rarer medium, okay, the refractor ray will bend away from the normal. Refractor ray will bend away from the normal. You have to remember these points. You have to remember these 2 points. Okay, will bend away from the normal. Away from the normal. Very important points. Very, very important points. You have to remember these points. Okay. And coming to our next topic, derivation of the formula for curved surface. For this purpose, I am considering a curved surface. This is a curved surface. Okay. And this curved surface acts as the interface between two different medium, that is denser medium and the rarer medium. On this side we have the denser medium. Okay, we have the denser medium on this side. Okay, and this is the pole of this curved surface, and this is the center of curvature, and I'm considering an object at point O. Okay, this is a point object, and I'm considering a ray which is moving along this principal axis. Okay, as the ray is moving along the principal axis, which is nothing but the normal for this curved surface, this ray will not deviate after refraction. This ray will move along this principal axis only after refraction. I am taking this ray as 1. Okay, and I am considering one more ray from this object, a ray which incident at point A, on the curved surface. Okay, and at this point, if this is the normal, after refraction, what happens? As the ray is moving from the rarer medium to the denser medium, the refractor ray will bend towards the normal only. Okay, and I am just extending this normal on the other side. If theta 1 be the incident angle and theta 2 be the refracted angle. If theta 2 be the refracted angle for this second ray, theta 1 be the incident angle and theta 2 be the refracted angle. And this ray 2 makes an angle alpha with this principal axis, and this normal makes an angle beta with the principal axis, and this refractor ray makes an angle gamma with this principal axis. Okay, and here we have the image. Why? Because the ray 1 and 2 after refraction meets at this point. Therefore, we have the image at this point only. Okay, and I am just drawing a perpendicular line from point A to the principal axis. I am just drawing a perpendicular line from point A to this principal axis, and this meets this principal axis at point N. And OP is the object distance. And PI is the image distance, which is denoted with V. Object distance is denoted with U and image distance is denoted with V. And PC is the radius of curvature, which is denoted with R. Now, using this figure, we are going to derive the formula for curved surfaces O. From triangle ACO, what I am doing is, here theta 1 is the external angle. From triangle ACO, theta 1 is the external angle. Right? For triangle ACO. Okay, and alpha and beta are the internal angles. Alpha and beta are internal angles, and we know that external angle is equal to sum of internal angles. What is the external angle? We have theta 1. Theta 1 is the external angle. This will be equal to sum of internal angles alpha plus beta. Okay, I am taking this as first equation. Okay na? External angle then equal na sum of internal angles. Okay, and external angle is the theta 1, and we have alpha and beta as the internal angles. దీనికి బాక్స్ కొట్టి పెట్టేసేయండి. This is equation number 1. And from triangle ACI, from triangle ACI. Here external angle is beta. Here external angle is beta and internal angles are theta 2 and gamma. Okay, theta 2 and gamma are the internal angles. So from triangle ACI, external angle is beta and internal angles are theta 2 plus gamma, right? From this, theta 2 will be equal to beta minus gamma. Then kuda oka box kottesi petteyandi. This is equation number 2. Okay. Now, according to Snell's law. What is Snell's law, Nana? According to Snell's law. Snell's law is nothing but the ratio of refractive indices. The ratio of refractive indexes N2 by N1 is equal to sine of incident angle, that is theta 1. Incident angle is the theta 1. Sine of refractive angle, it is theta 2. Refractive angle is theta 2. And from this equation, you just do cross multiplication. Therefore, we have N1 sine theta 1 is equal to N2 sine theta 2. Okay, this is equation number 3. Okay, now substitute equations 1 and 2 in equation number 3. Okay, now theta 1 value, theta 2 value equation 3 lo substitute cheste manaki em vastundi nana? N1 sine of alpha plus beta. Ona theta 1 value enti alpha plus beta. This will be equal to N2 of sine of what is theta 2? It will be beta minus gamma. It is beta minus gamma. Okay, this is equation number 4. Now, what I am doing is, as per the diagram, we have, this is a curved surface, okay, and we had drawn a perpendicular line from point A to this principal axis, and this meet the principal axis at point N, right? And this is the incident ray for point A. Okay, and this is alpha angle made by this incident ray with the principal axis. What I am doing here, I am considering the paraxial rays. Let's consider the paraxial rays. Let's consider the paraxial rays. What are paraxial rays? Paraxial rays. The rays which are moving very close to this principal axis and they are parallel to this principal axis. Okay, for example, I will draw here the rays which are moving very close to this principal axis, okay, and they are parallel to this principal axis are known as paraxial rays. Okay, if you observe carefully and if you draw a perpendicular line, from this incident point to this principal axis, what happens? This N meets with the pole P, right? This N coincides with the pole P, and not only that, here the angle decreases. The angle alpha becomes very small, right? Not only alpha, on this side we have beta and gamma, right? These angles also become small. That means angle alpha, beta and gamma becomes very small. Okay, this approximation is known as paraxial approximation. Paraxial approximation antam. Paraxial approximation antam. Okay. So as the angles as alpha, beta and gamma becomes very small, for small angles, sine theta or sine alpha, okay, sine alpha, sine beta and sine gamma. Sine alpha will be equal to alpha, sine beta will be equal to beta, Sin gamma becomes gamma. Okay, for small angles. But here we have sine of alpha plus beta, right? Sine of alpha plus beta. Here we have sine of alpha plus beta and sine of beta minus gamma. This sine of alpha plus beta, sine of alpha plus beta will be equal to alpha plus beta. Okay, and sine of beta minus gamma, beta minus gamma will be equal to beta minus gamma for small angles. For small angles. Okay, this is equation number 5. Okay, this alpha, beta and gamma becomes very small whenever we consider the paraxial rays only. Okay, substitute this equation number 5. Substitute this equation number 5 in equation 4. What is the equation 4 we have? N1 sine of alpha plus beta equals to N2 sine of beta minus gamma, right? This is equation number 4. Now you just substitute the value sine of alpha plus beta and sine of beta minus gamma in this equation. Therefore we have n1 alpha plus beta is equal to n2 beta minus gamma. Okay, now you just multiply n1 alpha plus n1 beta is equal to n2 beta minus n2 gamma. Okay, now I just want to find out the values of alpha, beta, gamma. For this purpose I am considering tan alpha and tan beta and tan gamma. From this figure, what is tan alpha, nano? Actually tan theta is nothing but opposite side by base, right? Opposite side by base. Therefore what is tan alpha we have? Tan alpha is equal to an by on. An by on. Tan alpha is equal to an by on. Tan alpha is equal to an by on. And coming to tan beta. What is tan beta we have? Here this is the beta, right? Here we have the angle beta. Tan beta will be an by nc. Tan beta will be an by nc. An by nc. And coming to tan gamma. What is tan gamma we have? Tan gamma is equal to, here we have tan gamma angle. This will, tan gamma will be equal to an by ni. An by ni. Tan gamma is equal to an by ni. Look at here carefully, Nana. For small angles, tan alpha will be equal to alpha, tan beta will be equal to beta, tan gamma will be equal to gamma. Therefore, from here we had find out the alpha, beta and gamma values, right? And this is equation number 6. This is equation number 7. Now substitute equation number 7 in equation number 6. Okay. Now substitute equation number 7 in equation number 6. What is equation number 7 we have? It is n1 alpha plus n1 beta is equal to n2 beta minus n2 gamma. And n1, what is alpha we have? Into n1 into an by on, right? Plus, and what is beta we have? n1 into beta is an by nc. This is equal to n2 into beta is an by nc, right? Minus n2 into what is gamma we have? an by ni. Okay, if you observe carefully this equation, on both sides we have an common. if you take this an common and you just cancel it on both sides. Okay, therefore we left with n1 by on plus n1 by nc is equal to n2 by nc minus n2 by ni. Now from figure, whenever you consider the paraxial rays, what happens, and whenever you draw a perpendicular line from the incident ray to this principal axis, this n coincides with p, right? And here we have the object, here we have the center of curvature, here we have the image, right? Then the value of ON will be equal to OP, right? ON will be equal to OP and NC is equal to PC, right? NC is equal to PC and NI is equal to PI. The value of NI will be equal to PI. Now substitute these values in above equation. Then we have N1 by OP plus N1 by NC is PC equal to N2 by PC minus N2 by what is Ni? It is PI. PI, right? Now you just keep it in a box. Keep this equation in a box. This is equation number 8. Using sign convention, what is sign convention? I had explained about sign convention in reflection of light chapter, right? Reflection of light at curved surface. Don't worry, I will also explain about sign convention here also. This is the interface we have, and here we have the object, here we have the center of curvature, here we have the image, right? And the direction of the incident ray is this one. Okay, and here we have the pole. And first point for sign convention is you have to measure the distance from the pole only. Okay, you have to measure the distances from the pole only. For example, OP is the object distance. We are measuring the object distance in this direction, right? But coming to the second point, whenever you measure the distances in opposite direction to the incident ray, here the incident ray direction is in this direction, but we are measuring the distance in opposite direction to this incident ray, right? Therefore we have to take it as minus sign. We have to take it as minus sign. And coming to the image distance, here this is the object distance, right? And coming to the image distance, we are measuring the image distance in the incident ray direction only, right? So here we are measuring the image distance from the pole itself, and it is measured in the direction of the incident ray. Therefore we have to take plus sign here. Okay, and whenever you measure the height of the image or height of the object above this principal axis, we have to take it as plus sign, and below the principal axis it is taken as negative sign. Okay, this is about sign convention. I am not writing the points here. You just pause the video and write the sentences. Okay, and here in this equation we have to know the value of OP, PC and PI. OP, PC and PI. Here what is OP? OP is minus U, which is the object distance. Okay, and PC is the radius of curvature denoted with capital R, and we are measuring in the direction of the incident ray only. Therefore I am taking it as plus sign. Therefore PC is equal to R, which is nothing but the radius of curvature. Okay, now and PI. What is PI? PI is plus V, image distance from the pole. Okay, this is the image distance from the pole. Image distance. Now substitute all these values in above equation. Substitute all these values in equation number 8. So from equation 8, what we have? N1 by OP. N1 by OP, right? N1 by OP. What is OP? It is minus U. Minus U, right? Plus N1 by plus N1 by PC. What is PC we have? What is PC we have? PC is the radius of curvature, right? N1 by R, which is equal to N2 by PC. PC is the radius of curvature R minus N2 by Pi. Pi is image distance, right? Which is denoted with V. Now what I am doing? I am just bringing the common terms on one side. Okay. Therefore, I am taking this N1 by minus U. I am taking minus sign here, U, and I am just bringing this minus N2 by V towards left hand side. Therefore, it becomes plus N2 by V. This will be equal to N2 by R, N2 by R minus N1 by R. I am just bringing this N1 by R towards right side. Okay. Therefore, finally we have the equation N2 by V minus N1 by U, which is equal to, I am writing R in denominator, okay, N2 minus N1. This is the final equation, equation number 9. Okay, this is the equation used to find out the relation between the image distance, object distance, radius of curvature, and refractive index of the second medium and refractive index of the first medium. This gives the relation between all these physical quantities, right? And this equation is known as the equation for curved surface. This equation is the equation for curved surfaces. For curved surfaces, this is the equation, right? Equation number 9 can also be used for plane surfaces. For plane surfaces, you can use this equation, but for plane surfaces, this R value is equal to infinity. Why? Because if this is the plane surface, the radius of curvature is at infinity. Okay, therefore 1 by R is equal to 0. Something by infinity is equal to 0, and this equation and becomes N2 by V minus N1 by U is equal to 0. If we substitute 0 in this equation, this will be equal to N2 by V minus N1 by U equals to 0. Therefore, for plane surfaces, we have the equation N2 by V is equal to N1 by U. This is the equation used for plane surfaces, and this is the equation used for curved surfaces. Okay.